year was that Subaru? What did I say in the video? Did I give the year of it?
95.
Was it that old? Let me see. I'm just gonna put the
1995 Subaru Legacy with a
2.2. All right, so a review of the 95 Subaru video. The ignition coil design, we had a main feed. I'm trying to think of the colors too. I guess we don't have to color coordinate it, but I had a main feed coming in, and then the controls. This would be the internals of the coil that obviously you're not going to see in the video. We're sharing a power feed, and there would be 2 coil control wires. The feed would have just come from, you know, some type of fuse that would probably be an ignition positive source. Not probably, it would definitely be ignition positive. In other words, when you turn the key on, you're gonna have power. The 2 controls would have gone to my igniter, and inside the igniter, let's see how I can draw this. Inside the igniter, there would be 2 transistors on this design. And the transistors would switch to ground. And this would be the wiring for that. And then what we had would be the computer, the PCM, or ECM, ECU in that year. I think they called it an ECU, electronic or engine control unit, whatever. We have 2 wires that go to the transistors. That's basically the wiring design for this. All right, so your question now, Nicole. I think maybe that will help where we were.
So because they're ground side switched, like the transistor, that's why you want the light on before you even crank it.
Correct.
Like on those things.
Yes.
But it flickers because of whatever.
Yes.
Because if it flickered, it would have been good, right?
That is correct.
So,
In the video, we were taking a test light and we were checking really in these 3 locations is where we started the video. And the test light was connected to ground, and the test light lit on all 3. So let's start with that. It lights on all 3 exactly because of what you said. It's ground side switched and there's no ground yet. So of course the test light's going to light on the feed wire, and the brightness of that light on the feed wire would be important. And we compare it to the 2 control wires, so we were checking the same thing here, checking the same thing here, and the brightness was the same on all 3. Now, maybe to address that part first, why would the test light on the control wires be just as bright as the feed? Why is the brightness the same? The answer is the coils are low ohm coils. A primary ignition coil in general is around 1 to 2 ohms of resistance. It's a very, very low ohm coil. Our test light that we're using is very high ohm.
so when you tested them with the light to begin with, you couldn't say that. You could say the first time before you even checked the igniter that the wires were good, right? Because they all lit.
No, okay.
Or was that because?
The only part we've tested so far, Nicole, would be the feed coming in. Let me get a different color. Let's use blue. The feed coming in, and then the coils themselves. This is as much of the circuit that I've checked so far. Just with the key on, I've not gone any further. So it's the feed circuit that would be good, and then just to there. We're not really checking these control wires yet because we could have an open here and those lights would still light. So we haven't checked those controls yet. All we've looked at is the coil itself. Now when we crank it, we're looking for 2 things. One, we want to see a distinct difference between the power feed wire, which is this one, and the control wires, which are these ones. The reason we want to see a distinct difference is the control wires should be switching on and off, right? And when they switch on, our test light should momentarily go out, and when they switch off, the test light would be bright again. That's what's going on when these transistors start switching on and off. We're pulling the circuit to ground on both sides. but it's such a momentary event that that test light isn't going to actually go off and turn back on like a switch would. Like if you picture a light switch, I flip the light switch off and then flick it back on. The lights go out completely and then they come back on. Why doesn't that happen here? It's because it's such a fast event. The second thing, the reason we want to check the feed while we're cranking, and I mentioned this in that video, is I want to make sure that system voltage, remember that we have system voltage being supplied in here, and we're cranking an engine over that's a no spark, no start situation, so we're relying on starter current to move the crankshaft. And when we did relative compression tests, you remember these humps that the starter amperage produces, and we can have as much as an 80 amp surge from the top to the bottom, anywhere say 40 to 80 amps. With that kind of surge occurring, doesn't voltage follow that? If you were to graph system voltage on a scope, you would see the same event zoomed in. Remember how we zoomed in on the map sensor on the Hummer and we saw the map oscillations? If we were to zoom in on battery voltage on a scope when we cranked it, we would actually see the same thing. So just maybe a side note, we can actually do relative compression testing just by going straight to the battery and just cranking it over, looking at a voltage waveform. But voltage would follow that. As amperage would rise, voltage would drop. And so the voltage waveform would be exactly opposite if you think about it. High amperage, low voltage. Low amperage, high voltage. That's at the battery. Could this stuff going on here, could this affect what the test light looks like here on the feed wire when we're cranking? Could that make that test light kind of almost look like a flicker? That's what we're looking for control. So that's the second reason we check this, like this cranking, check that feed wire cranking, compare it to the control wires. They should flicker. And they didn't in the video. That's where we are so far. Does everyone understand why the test light, and I kind of skipped past this as my magic pen was not working. Does everyone understand, hang on, why the test light is just as bright on the control wires as it is on the feed? Do you remember this conversation of having a resistor here and a resistor here and then ground, and then where are we putting our test light? Our test light is this resistor, isn't it? I'm going through the winding here. This is the first resistor in my picture, and the test light is the second resistor in the picture. So we have 1, 2. And what we did earlier in the term is we put this at a low ohm number, and our test light is high ohm. And what we said is that there is not much of a voltage drop that occurs here. We used some Ohm's law to determine how much voltage was in the middle up there. Do you guys remember this conversation? Do I need to do it again? Okay. Low ohm here would be high voltage in here. We don't have much of a drop that occurs here. That's why my light is bright. Because let's say that you connect this light like this. There's 12 volts on the tip of this light, and this is ground, so of course the light's going to be bright, and maybe on this one here it might be like 11.8, and this is 0 here. So are you going to see a difference of 0.2 of a volt between that? No. Is that test light supporting enough current flow to energize that ignition coil? Not at all. That's not what we're doing here. If this was a high ohm coil here, like say a relay coil, which is like 80 ohms of resistance, do we have a large voltage drop that's going to occur across 80 ohms here? And the answer is yes. So the voltage in this middle section in here is going to be low volts. And the test light, which is set up here, may not even light. There may only be 2 volts left in this middle section. And so if this was a high ohm coil up here, and this drops down to 2 volts, is this light even going to light? The answer is no. And so just a little lesson on the test light and the brightness of that light.
Would you have to use the incandescent one for these testings? You couldn't use the ones we got, what is it, the LED or whatever?
That's a good question. Can we use the LED one for this? I'm fearful that we may actually burn out the LED test light.
Okay.
And the reason why, if this primary circuit is working, we'll have 300 plus volt spikes that are going to occur in there. And I am fearful that that may burn out the LED type test light. I'm not totally sure about that, but I would hesitate to use an LED test light on here just for fear of ruining my test light. So I would prefer an incandescent type test light for this, I think. But I don't know. Maybe I'm wrong. We could try it. Want to use your test light later today?
But they were
You have one.
stuff. Oh,
It's
just a bulb, right?
No. If you
Oh.
burn that out, it's the whole circuit board. Like that LED bulb is soldered into a little miniature circuit board,
Yeah.
so it's not like
Oh, bulb will be here tomorrow, right?
Yeah, you
Let's
can
try
just-
it.
trade it in.
Yeah.
I'm not sure. Maybe we could use the LED one here. I prefer my incandescent. Either way, it's going to work the same way. As long as we wouldn't burn out the LED bulb in doing this, you can use it. It will work the same way. It might even be more. Yeah, see, I don't know. As I'm thinking about that, would that LED bulb give you a flicker like a regular test light would? Now, use a regular test light when you're doing this. Now, there's some variables with the LED that I'm not sure of. All right, in the video, did you see how all 3 look the same? So with all 3 looking the same, doesn't that tell us we have no control on that circuit? That's what I'm saying in the video. This is control testing with a test light. No control on that circuit would move us away from the ignition coil. That's this piece right here. It would move us away from the coil, and it would put us toward the igniter. And it's either OR or ER. Spell check doesn't work for igniter, and I've seen it spelled both ways, so take your pick. Igniter. The igniter on this model, I think it's important to know some of that too, but I don't know how much I want to go into that. This igniter is one that cannot function outside of the engine computer. In fact, there was actually no power feed on this at all. These grounds would tie in on the board, and then it was grounded externally. So there was only 1, 2, 3, 4. There was only 5 wires going to this igniter, if I remember correctly. No power feed at all. What's in the igniter is simply 2 transistors that control these coils. So what did I do next? In the video, I brought my test light up to here. I brought my test light up to here, and I brought my test light to here. What was I looking for? What was the purpose of that test? Moving them from here to here. What part am I trying to isolate? The wire. Very good. If I had opens in this control wire, either here or here, would that make these lights not flicker over here? Measured here. If there was an open here and an open here, wouldn't that make these lights here be steady and not flicker? The answer is yes. So when I move my lights over here, the fact that they are lit just as brightly as they were over here tells me what about the control wires? Tells me they're good. That was the purpose of that. Moving the lights over there. So how's my control wires? They're good. Next step, we focus on the igniter itself. Knowing the system design was important, that this system requires the engine computer to tell the igniter what to do, if you want to call it that. The igniter on this one, I would call this one that is not able to work on its own. It has to work with the engine computer. Engine computer is responsible for sending the signals. In the video, I switched my tools, and I think I showed you first that you can't use the test light on these circuits. And I believe I even hooked the test light up to those, and nothing happened. When I put my test light here to ground and here to ground, the light was off when we cranked it over. What was I looking for, by the way, in this? What am I looking for? Knowing how transistors work. What do we need for the base of the transistor to turn on? I need some type of small voltage signal. I'm looking for an on-off control. For a transistor to pass current, we don't even have to draw the polarity here. For a transistor to pass current through the collector and emitter circuit, we have to have a small voltage on the base. We have to turn this base on with this NPN type transistor. We have a small positive voltage on the base to turn this on to allow flow. So I know that up here, I need flow through this transistor to ground, which will create the magnetic field on my primary coil. Needs to switch to ground. I have to have some type of signal. That signal comes in here. I put my test light on that, and it did not work. This is where the LED test light may actually help us. I'll bet you, Nicole, if we would have put your LED test light in this place, we would have seen a flicker of the bulb, which would have told us the computer was fine and that we have an igniter problem, like in the video. I switched my tool knowing I'm using an incandescent light, that I couldn't use that anymore. And what I did from this point is I put a graphing multimeter, just my old Vantage, my Snap-on Vantage on here, and I saw square waves on my two igniter control circuits. So if I see those square waves there, what does that tell me about the cam and crank signals coming into the computer? They're good, and I never even tested them. If I didn't have square waves there, what would have been my next step? Cam and crank. So do you understand what I was doing in the video now? When I switched my tool and I checked for those signals, and I had square waves there, and they were 0 to 12 volt square waves. So some of you might be thinking, hey, that's 12 volts. Why didn't that light the test light? Well, it's 12 volts, but it's going across the resistor inside this computer. I promise you there's some resistance. It's a 12 volt signal that's being sent out, and when you put your test light on that, it pulls it to ground. So it's a high resistance circuit. You know, it's just like having a circuit like this. If we put 12 here and run it across, say, 1,000 ohm resistor, and we measure the voltage here, what do we read? We read 12 volts. As soon as you put any kind of a load on this, if you were to, say, put a test light here to ground, we're going to pull a lot of that voltage down, and maybe that's like 1 volt. So that's kind of the analogy of what the test light did on that circuit. Can't use the test light. At this point, doesn't this also tell us that my computer is fine? So it tells me my inputs are fine, tells me my computer is fine. We did our checks here and here, which told me what? Told me everything from here over is good. What are we left with? There's one more check before we put an igniter in this.
Ground.
The ground. And that ground is shared by both of these transistors. The igniter board, so I have it drawn like this because the entire board, like all of this in here, would be grounded. So when the transistor turns on, it grounds to the housing, and then the housing's grounded external. If we had an open in the ground, would you guys agree with me that we would be in the exact same scenario we are right now? If my ground was open, would these transistors be able to switch to ground? They would switch on when the base signal is there. They would complete to ground. But is there a ground if the ground's open right here? No, there's not. So what happens to the voltage level on this entire board when, as soon as the transistor turns on and we switch this 12 volts to the board, which we want it to pull this to ground, doesn't the entire board itself contain 12 volts as soon as that transistor turns on? It does. So in the video, what I did, knowing that an open ground would do that, I simply put my test light to ground. Or did I switch it to power at that point? Did I switch it to power? There's two ways to do it. We can leave it on ground. Some of you are thinking, well, of course the test light's not going to light. You'd be right. Test light should never light. If I'm ground here and ground here, that light should never light. But when would it light? When I'm cranking. Why only cranking, Nicole?
Because that's when the transistor's on.
Correct. When is this ground circuit loaded? Would be when we're cranking, when those transistors are turning on. If that ground was open, that light would have lit up at that point in time. In the video, I switched it to power, which can be done that way too. Switch this to power, my light lights, okay, telling me I have a good ground. Not a good test yet, because it only takes 200 milliamps to light my test light bulb brightly, where those coils draw 6 to 10 amps of current apiece. So in comparison, 200 milliamps is what? 1/5 of 1 amp. And these coils draw 6 to 10 amps. So there's 1,000 milliamps in an amp, right? 6 to 10 amps would be 6,000 to 10,000 milliamps a piece. Way more of a load than my light is. If we have a ground problem, as soon as we start cranking it, doesn't pressure back up in this entire area. And where I have it green, wouldn't voltage rise as we cranked it? It would. And so we have 12 volts on this tip of the test light, and for this light to light brightly, we want 0 volts, but is this section going to be 0 anymore? No, it might be 11 volts. And now does my light stay lit when we start cranking it? The answer is no, it goes out. And that would be a bad ground with your test light connected that way. You guys follow that? So there's two ways we could have checked that ground with the test light. Is the test light the ideal tool for checking the ground? No, that was the point of that video, was showing you how to address this circuit with a test light. So anybody can do the troubleshooting on this. All right, I added something else. After we addressed the ground and we said, okay, those are good, or maybe I did the ground last, I'm not sure. What I added was, because I was thinking of those of you that don't have a scope. You guys don't have a scope yet. So what I did is I put the voltmeter on the control signals, and I think I'm a little bit out of order in when I did that. I was trying to show what those 0 to 12 volt square waves would look like, because they look like this on my graphing meter. When I saw them across the screen, I wanted to see, would it be possible to use a voltmeter and a test light only and be able to make the same call? And the answer is yes, but we didn't see 012s on our voltmeter, did we? What did we see? I remember seeing maybe 2.1 volts. At some point in time, when I was cranking it, we saw around 2 point something. Why were we only seeing 2 volts? Because a voltmeter will average a fast on-off signal. And you might be thinking, well, the average of a 012 is 6. No, you'd be wrong. Because we are look how much lower we are, or time-wise, look how long we are low compared to how long we are high. The average is going to be much closer to ground than it is to 12, and that's why our voltmeter was reading 2 volts. And so I guess what I'm saying to you guys is it is possible to use a voltmeter to make that call, but it's a little bit, it's not as good of a test, is it?
So if it was higher, you know, at like 8, 9, 10 or whatever, there'd be opens somewhere?
No, that's a good
Or-
question. That's a great question. If the voltage was higher on our voltmeter, would we have a problem, is basically what you're saying. The answer would be no, because couldn't the signal be something like this? If my signal looks like this, do you see that my on time is now longer than my off time? And so my average voltage is going to be up here now. This might put me at like 8 volts. Is that a problem? The answer is no, it's just a different characteristic. Every car is different, and you won't know that. Every digital signal is different, and you won't know that. Here's what we're looking for this test. I'm not looking for a specific voltage level. I'm looking for something that tells me there's activity on this circuit. That's all. And it is not a foolproof test. Because how do you know with a voltmeter if your 8 volt reading you have is from an average, or the 8 volt reading you have is a flat line 8 volts? Unless your meter has a very fast min-max function to it, you're not going to know. And that's why I don't like that test. So now we have questions here on this car. Okay, hey, I have 8 volts on this wire, but what if it's a pull-down design circuit that should be switching to ground and it's not, and the steady 8 volts is just no activity? I don't know. This is where I would want a scope to see that. Or maybe your LED test light might be ideal for that maybe we can see some flickering. I don't know. There's always questions. There's always questions when it comes to this. We can use it, but there are certainly more variables with the regular voltmeter. So at this point I said, all right, bad igniter, but there's one more check I want to do. And in the video, why did I want to do this one more check? I was concerned about a shorted winding in the coil. Now, the chance of having 2 shorted windings are slim to none, but what I did is I connected an amp probe here, and I connected an amp probe here. And I cranked it, and I had flatline 0 amps, which confirmed no control. I need to take you to a case study here in a second in my book. But before I do, let me ask you a question. How do you like the test light, what I call, quote, control testing? How do you like the test light so far? It's pretty nice, right? We just look for a flicker of a test light. You guys know that we can use this same procedure on a 1950s vehicle all the way through everything that we're doing. It's a pretty cool test. Is it 100% accurate? The answer is no. It's not. So let me take you to, this is section 22 where you guys are. I want to take you to a case study I have. What we're dealing with this case study is an engine computer, and I'll just draw 2 different coils. This is a coil over plug ignition system. The coils are externally powered, and internally they're switched by transistors that live actually inside the computer in this case. There is no external igniter or module on this car. And by the way, I am drawing only the primary circuit of these ignition coils. So we're clear, an ignition coil has a primary winding and will also have a secondary winding that wraps around the primary, and the wiring for the secondary can change as far as where they put it and everything. There's 2 separate windings, but I am focused on the primary. Why? Because the primary is what controls the secondary. When we talk about coil control, we're talking about the primary side, not the secondary side. So our focus is on the primary. In this case study, I have a dead misfire, okay? And I have two separate coil negative control wires that I'm looking at. So my scope is connected here, and my scope is connected here. Okay? What do we see? I see 0 volts here and 300 volt spikes over on this pattern. So on-off control. This is what we'd want to see on a scope. If you're zoomed out, I don't see the detail because, you know, I would need to be in on this kind of time base to see the detail there. We're just kind of a zoomed out view. Is there control on this coil to the left? Yes or no? By control, I'm saying, is there pulsing? Is this coil being turned on and off? Is there control? The picture to the left, yes, most definitely. The picture to the right, here's 0 volts, here's 50. That looks like, if I would break this down, that's about 12 volts. 12 to 14 volts. It's a flat line. Is there control on this coil to the right?
Yes.
Why do you say yes? When we talk about control, we're talking about switching the coil on. Here's what happens, look. I'll draw it as a switch this time. What's the voltage in here with the switch open? This is my control wire. What's the voltage in this section, this control wire with that switch open if my source is 12? It's 12. And when this switch closes, what does this 12 volt line do? Goes to 0. And as long as that is closed, we will stay low. And what happens when the switch opens back up again? We come back to 12. Except in here, that is not what happens. What happens in that section? We get this huge voltage spike from what? From the collapse of the magnetic field. When we look at control, we want to see a big spike. What does that tell us? There's control. When we don't see that over here, there's no control on the picture to the right. There's no control. There's no spike. Does that make sense? What would the test light look like if I connected up to this circuit? Would it flicker? Yes, it would. What would the test light look like if I connected to this circuit? Would it flicker? No, it would not. Okay. This is the whole point of where I'm at with this case study right now. What's the test light going to do? Next step. I went to those two. See if that picture comes back. I went to these two and I connected an ammeter to both so I could look at current flow. And I looked at current and voltage at the same time in the next capture. What do we see? This is what I expected to see over here. I expected to see my amperage pattern line up with my voltage pattern. We turn it on, voltage drops, current starts. We turn it off, voltage rises, current stops. Did I say that right? Did I? We turn it on, voltage drops, that's when current rises. We turn it off, that's when voltage rises because it's ground side switch, current stops. So they're timed together. We have control. We already know that on this left picture. What the heck is that? That's showing me what? Showing me control. I have amperage here. But wait a minute, if I have amperage, why don't I have a voltage drop that's occurring at the same time? Because that doesn't make sense. Okay? Next page. We need to zoom in on one of these a little bit more, zoom in on one of these a little bit more, and get an idea of what we're looking at. This is what we're looking at. Picture to the left. That's a good looking coil current ramp. We did some coil current ramp stuff the other day. We talked about the counter electromotive force, the counter voltage that causes a ramp effect. We want to see that. This is a good looking waveform over here. And we look at this one, and guess what? I do see some activity in there that I couldn't see on that other scale. What else do we see? A straight up line on an ignition coil is a shorted coil. That coil winding is shorted. Questions so far? I'm not done, but just for where we are. Helped to have that conversation, didn't it? Our coil primary current ramp testing. All right, one more. Let's zoom in one more time. I really wanted to focus on this. Is there coil negative control? Is my question to you. Is there coil negative control? The answer is yes. Why did my test light back on the first page, back on this, why did my test light not flicker? Because I'm only changing from, here's my levels. 13.9, 12.6, so this is cursor X, this is cursor 0. So I'm changing 1.341 volts. From this line here to this line here, I'm only dropping 1.3 volts. Is a 1.3 volt drop from 13.9 to 12.5 going to change what my test light looks like? Not a chance. Does my test light flicker? No. Is there coil control? Yes. Is the test light always accurate? No. Is it a cool test? Does it work great? Yes, unless the coil primary winding is shorted. Am I making myself clear? Do you understand in the Subaru video why I put an amp probe on those two wires now? I want it to be 100%. What are the chances of that Subaru coil having two completely shorted primary windings? Slim to none. But was it important for me to show in that video all of the variables and possibilities? What's going on in here? The best description I can give for you would be a transistor that's switching to ground. We know that, right? This transistor is protecting itself by limiting current on the ground side, which would be what I'm calling an intentional, I've said this many times, an intentional bad ground. We're adding resistance so we don't burn up that transistor. If we add resistance here, let me extend this ground here. If I add resistance on the ground, won't that cause pressure to back up this way? Won't I get a pressure rise in this area from this added resistance? The answer is yes, that's what's going on. We're protecting this transistor. With a 1.3 volt drop and very, very high resistance on the ground, that's what that's telling us. We are still carrying, there's a conversion factor here. This would be 4 amps, 8 amps, this would be 12 amps. We're still carrying roughly 10 amps of current flow on that coil. Why? Because the coil winding's shorted. Now I've used this case study for a long time. Right now what we're emphasizing with this case study is that test light. Will that test light always be accurate? It will not be. Okay? Can we use it as a guide? We can. In fact, most of the time when you do this, probably 9 times out of 10, maybe 9.5 times out of 10, that test light is going to be accurate, but sometimes you're going to have a shorted coil that makes it not accurate. Any other questions on this Subaru, on this thing and what we were doing, and why I added those two tests at the end? Everybody comfortable? All right, we'll go take a break.